While I get your breakout rooms ready to go for today's activities in lab, let's get some of the logistics of the day taken care of. First of all, you'll have your Unit 1 assessment next class. There will be 3 targets covered on this assessment, and they're listed in the box up above. As you'll notice, they're the things we've really been doing in class. Elements, compounds, and mixtures using our chip models, drawing pictures of chemical reactions, and then using those pictures to check on the conservation of mass. You have 2 resources to help you get ready for this test. The first one is your portfolio. By the time you're done with today, you should have 6 entries in your portfolio. Each of those entries details what we did on each day of class, as well as having some closing questions to help you determine whether you really understood what went on that day. Be sure that you finish all 6 entries of the portfolio and submit this portfolio via Schoology before you return to class the next time. Your other resource for preparing for this test is now in Schoology. One of the last folders in Schoology is a folder labeled Practice Tests. There's a Unit 1 folder in there, and the document you need is this link right here, Unit 1 Practice Test. You can either work this thing as a digital document by making a copy of it and typing your answers directly into there, perhaps drawing the pictures on a piece of paper, taking a picture and inserting them. You can print the document and answer the questions directly on the document, or you can do some combination of those 2 things. If you need to, you can simply work on a separate sheet of paper and take the pictures when you need to get them submitted. As you finish each page of the practice test, or when you've completed the entire thing, there's a folder for each page where you'll be able to submit your work, see an answer key, and then make corrections. While the practice test is not required, the practice test is like insurance for your test. The practice test must be completed, submitted, and all corrections made in order to earn the privilege to reassess shortly after the Unit 1 test. Much like car insurance, we hope that you're not going to have to use it. If you've kept your portfolio up to date, you've completed and checked and made corrections to your practice test, hopefully you won't need to use the reassessment privilege anyway. However, just like you wouldn't drive your car without insurance, you don't want to take your chem study test without insurance either. Choosing not to do the practice test will mean that your reassessment will have to wait until the end of the semester in January on your final exam. The other thing we need to do in preparation for your test is go back and look at that checkpoint that you took in your last class about the little kid's volcano and the formation of precipitate reaction. While I can't get this back to you because of our current condition, we should look at this so that you have some idea what a proper answer for this would be. If you need to pause the video at this point to read the question, feel free to do so. When you read this paragraph, there are a number of things that you need to consider before you get ready to answer the question or draw the picture. The list is below in blue. Vinegar is a mixture. That means that it's going to need 2 types of particles. That comes from this sentence right here. Household vinegar is a mixture containing vinegar and water. The second thing to consider is the foam and bubbles produced by the reaction. This is an indication of the formation of something new. From the particles you start with, you need to assemble something brand new. Observation 3. Foam pours out of the top and stuff gets out of the volcano. When you draw your picture, you need to draw something outside the volcano, inside that little pan. Number 4. There is some liquid that remains in the beaker. That means that your beaker needs to still have some of those water particles. The next observation is that the liquid no longer smells like vinegar. Whatever you chose as your representation of vinegar particles, they need to be gone from the beaker and really gone from the liquid in the pan as well, because the odor has gone away. There's no solid present. This is an indication that baking soda is not still present in its original form. Whatever you used for your baking soda particles, they now need to have reacted with something else to create something new because they're not there. All the liquid is in the pan. This tells you that all the water particles that were in the volcano originally need to be distributed between the beaker that's in the volcano and the pan next to it. And lastly, the bubbles pop. This tells you that a gas that didn't previously exist escaped the volcano and went away off of the balance. This last observation tells you that the mass on the balance should decrease because some particles escaped as a gas. There are many possible ways to represent this particular reaction. I've chosen an extremely simple model. You may have come up with something a little bit more complex. I came up with a model that used 3 different types of particles: water, baking soda, and vinegar. In the beginning, I put the vinegar and water particles in the beaker and the baking soda in the little pile. In my model, the baking soda particles and the vinegar particles attached to one another to create a gas that was produced by the reaction. The gas being neither vinegar nor baking soda anymore, but the combination of those no longer smells like vinegar and is no longer a solid, and it constitutes the gas that left the volcano, accounting for the decrease in mass. My water particles, some ended up in the beaker, thus the observation of the remaining liquid, and some of them came out of the beaker and ended up in the pan when it bubbled over. I think that pretty well explains how my picture matches my prediction. Your picture may have looked slightly different than that, but needs to capture the key ideas from up above. The second half of this was an alternative model of the mass of a precipitate, where you mix the 2 clear colorless solutions together and you form a white cloudy precipitate that begins to settle down into the bottom of the beaker. There were 3 different levels that you had to assess this on to decide if it worked. First of all, does the model account for the formation of the precipitate? It does account for the formation of the precipitate because there are new particles that weren't here before. There's a purple-yellow combination and there's a green-red combination. Those must be the particles that represent the white solid. As far as showing conservation of mass on the macroscopic level, if I add up the sum total of the 2 containers before the reaction and the sum total of the 2 containers after the reaction, I find out that those 2 things are equal to one another. This little bit right here represents the water and the particles that get left behind when you pour one beaker into the other, and they would account for any mass that might be missing from this beaker over here. Does this model show conservation of mass at the particulate level? Indeed it does. If you were to go through and count all of those chips, you'll find out that the total number and proper colors of chips exist both at the start and at the finish. So while I can't get your checkpoint back to you, this should give you some idea what an appropriate answer would have looked like, and you probably remember enough about doing this that you know whether you did a pretty good job with your checkpoint or not. The next thing I'd like to do as we set up class here today is to review some ideas about the chemistry particles. This is in your lab, How Chemists Separate Stuff, that we started last time with parts 4, 5, and 6, and we'll be finishing this time. If you need to, pause the video while you dig through your folder or open something on your Schoology from the last class in order to get this handout back again. This lab was about, at least the part we did, was about putting some names with the chemistry particles. Some key features that you should have learned this last time is that when we talk about atoms, we've kind of updated our model here so that one chip now represents one atom. This is a little fancier model than was needed to answer your checkpoint question, but is generally the model that we will use from this point going forward. We added the word molecule to our vocabulary. This is a combination of atoms, and we're going to represent this by 2 or more touching chips in our model. So when you put 2 chips side by side, they will constitute a molecule. So atoms make up molecules, and between atoms and molecules, we have all matter in the universe. Anything that has mass occupies space, or anything that we can represent with our chips. Matter exists as one of 2 things. A pure substance. The key feature of a pure substance is that it has a single chemical formula to describe it. Only one type of particle will show up in our model if we're working with a pure substance. Via physical changes, which you will see some today, you can turn pure substances into mixtures, and you can turn mixtures back into pure substances. A mixture is a physical mixing or stirring of 2 or more pure substances. When you look at a particle level picture of a mixture, you will notice more than one type of particle present in the model. Pure substances come in two different varieties. Pure substances can consist of elements that are composed of a single type of atom. This is everything found on the periodic table. A particle level picture of elements would contain only one type of chip. In your situation, you had the possibility of the 7 green chips, or this collection down here that consisted of 3 B2s. Because all these chips are blue, you know that this is still an element, even though it's diatomic. Our compounds consist of 2 or more elements combined in a specific ratio. Within our models, these consist of collections that have only one single type of particle. This particle contains 2 reds and a white, but every one of those particles is identical. In order to qualify as a compound, the particles have to contain more than one type of element. Mixtures, which can be created by taking pure substances and stirring them together in such a way that they still look the same on the particle level and could be separated from one another, can consist of 3 possibilities. There's the possibility of elements with elements, which we have right here. This was the 2 yellows and the 3 P2s. You could have elements with compounds. Here we have 2 blues, some yellow and green. And over here we have compounds with compounds. And so here we have 2 different varieties of compound in the same container. Once we had laid down the vocabulary and had a spreadsheet to help us understand this, we were able to go on to matter 2. Part 6 involved practicing with some of these ideas. I would encourage you to get out a different color so that you can make some corrections here to your work. So the 4 containers here in question number 1, we have to identify the mixtures and the pure substance. Remember that pure substances would be a box that contained only one variety of particle. So box A and C are the pure substances, while boxes B and D contain a couple of different types of particles, and so those would represent mixtures. The boxes which contain only compounds are A and D. Box C contains only elements, and I didn't use box B at all in this part of the question because it contains a mixture of compounds with elements. Moving onward to the second box, we had to decide which were mixtures and which were pure substances. I chose B and C for my mixtures. In B, I have 2 different types of atoms. I can tell that this isn't a compound because I don't have a fixed ratio between the lights and the darks. It just appears to be a pile of lights and darks stirred together. C is a mixture as well because you have more than one type of particle. Box A is an interesting box. It represents all of those compounds that come as little crystals or little cubes. One of the ones you're most familiar with is table salt. When the salt falls off your French fry and onto the table, it consists of little bitty cubes. Those cubes consist of a very consistent patterning of alternating sodium, chlorine, sodium, chlorine, sodium, chlorine. And within here, we have a fixed pattern or a fixed ratio. So your crystalline compounds that look like little cubes are represented by a picture shown in A, but that is considered to be a pure substance. It is different than the picture in B because of the patterning and the very fixed ratio between the 2. The other pure substance here is D. This is the solid form of some variety of element. Of these, our compounds are A and C, and our elements is B. We have this darker element and this lighter element, and over here we have D, which contains entirely one type of atom. B consists of elements, although it's a mixture because it is in fact a mixture of elements. And in number 3, considering the 4 containers below, our compounds are in boxes B and C, Notice how the picture of box B has changed so that now the two pieces are hooked together in a 1-to-1 ratio and every particle is identical, unlike box B above, where the elements were simply stirred together. Box C also contains compounds. Elements would be A and D. Based on our drawings from our density, we can also figure out that A and C, where our particles are very spread out, are intended to represent a gas, and kind of the chaotic look of B is intended to represent a liquid, and D is intended to represent a solid. So make any corrections that you need to make to your work there so that you have something that you can work with as you prepare for your test. So that takes care of the logistics. Now you can leave Edpuzzle, return back to Zoom once you have all of your Edpuzzle questions answered, and hopefully by the time you return, I'll have your breakout rooms ready to go for today.